Okay, a brief summary again. We'll put our brief summary symbol up here. Maybe I should have used B5 instead of BS, I don't know. Okay, matrix A reduces to this. That means here's its row space. Its null space, well, we only have one equation if we do the AX equals 0, or this matrix times X equals 0. Right there is the only equation we get. We have three variables, x1, x2, x3. x1 doesn't even appear in the equation, so x1 could be anything. x2, well, one of these is going to be a free variable. x1 is a free variable, either x2 or x3 is going to be a free variable. We choose x2, call that t, so that x3 equals negative 4t. Excuse me. x1 can take any value. I can say it can be anything. Well, no, it can't be a tree. It can take any value, and that probably would have been the better way to write that down. So we let x1 equal s. That's not a 5, that's an s. A variable, a symbol, and get a basis for our null space. Okay, the basis that I get out of this, I choose to put the s for x1. Now, as long as x1 is s, well, okay. I'm going to let x2 and x3 be 0 when x1 equals s, so I'm just going to get s0, 0 for one vector in the null space. The other will be the vector that's restricted by t, 0t, negative 4t. Now, that works for any s and t you wish to use. I'm going to let s equal 1, t equal 1, and that is going to give us a basis. My specific basis is then going to be 1, 0, 0, 0, 1, negative 4. We can see that 1, 0, 0 is a vector in this direction. 0, 1, negative 4 is a vector down in this direction. So our plane is like this, and our null space is that plane. Okay, our row space is just all the vectors in the direction of 0, 4, 1. And that vector is perpendicular to this space. We can verify easily dot product of this with this is 0, dot product of this with this is 0. Okay, now if we remember A reduces to this, so A is some matrix that reduces to this. So by doing row operations on this matrix, we can build it up into a matrix that doesn't have the rows of zeros. So right there is a matrix with the rows of zeros. I asked everybody to do it. Everybody seemed to have gotten a good one. And this is different than what anybody else got, but we get the idea. Okay, a basis for our column space. Well, the leading one, if we take this one more step and divide the first row by 1, leading one is going to occur in the second column, meaning the second column of this matrix, if this is our A matrix, is going to be a basis for the column space. So this matrix will lead to this column space. And it's clear that this vector has to be in the column space because column space consists of all the vectors that we get when we transform vectors of V into W. Okay, if the transformation is defined by this matrix, if I multiply this matrix by 0, 1, 0, I get 4, negative 12, 1. So 4, negative 12, 1 is in our column space. It occurs over there in the other vector space. Specifically, if T is the transformation from V to W, where V and W are both R3s, as they have to be because this is a 3 by 3 matrix, the definition is going to be T of V equals A times V. So the transformation is just multiplication by the matrix A. Okay? So the row space and the null space occur in V, and the column space occurs in W, as we've seen previously. So we have a null space plane like this. We have our column space, our row space, which is like this, and the two are orthogonal. And then I think you're asked to pick a vector in the row space. It's got to be some vector, some multiple of that vector, and transform it and see where it lands in the column space.